Assignment 2.2, Part 3 by Samuel Marsh. Lactate/energy system analysis. For lactate, our hypothesis shows that no lactate should be present in the bloodstream. This is due to the fact that the client should be working aerobically on a steady state exercise, and as a result has no byproduct of lactic acid. In order to measure the energy system, we used a lactate machine. This involves using a pin to pierce the client's skin on their finger to get some blood. Then, we wiped it onto a piece of purta that gets inserted into the machine, and then this shows the result. In my group, we took this reading 2 times, at 3 and 18 minutes, whereas the other groups did it at 3, 8, 16, and also 3, 12, and 18. As per Kyle J. Gunnison, the normal blood lactate concentration in unstressed patients is 0.5 to 1 mmol to the L. This is the normative data, and assuming this is correct, our clients are not working in steady state exercise but in the anaerobic training zone, due to their average being from 14 from 0 to 3 minutes. This may be because of them increasing the intensity of the work. For example, in an attempt to increase their heart rate to the necessary training zone, the aerobic one, the clients may have sped up and worked too hard to get there to it too fast, rather than a slow increase like they're supposed to do. This sudden increase in intensity reflects the anaerobic system, and as a result increases the lactic acid in the bloodstream as it's a byproduct of it. However, at 12 minutes, the level has dropped down to 7.4 mmol to the L. This is a drop of 53%, which shows that the clients are beginning to work aerobically in steady state exercise, reducing the intensity so it plateaus and also reducing the lactate levels in the blood. Furthermore, from 12 minutes to 18 minutes, the average lactate levels drop to further 5% to 7, which again adds to the argument that they are working aerobically rather than anaerobically now, against the normative data. With the normative data. This basically supports our hypothesis that they will be working aerobically during the event and that no lactate will be present in the bloodstream. Working anaerobically, what they did at the start, potentially due to poor instructions by the rest of the group, has a byproduct of lactic acid, and, as a result of this, it began to be present in the lactate test we did, which may cause anomalous results on the graph. Whilst Evelin's and Oishin's graphs support our findings and almost our hypothesis and normative data, we do have one of the graphs does have different results from normative data. For example, on Morgan's graph, she works too hard up until 8 minutes on the heart rate graph via the anaerobic energy system, meaning that the lactate has been produced into the bloodstream as it's a byproduct. This can be supported by the heart rate graph just mentioned, which shows her heart rate graph will increase up until 8 minutes due to the fact she isn't working in steady state exercise but instead in the anaerobic energy system. We would have expected her lactate to not increase at all, or very minimal at that, but due to no lactic acid being produced as it's aerobic respiration. So the review of the lactate energy system is that the average lactate between all 3 of the clients between 0 to 3 minutes is 14. The average at 12 minutes was 7.4. The average between 16 to 18 minutes was 7. The average decrease from 0 to 12, which shows that they were working anaerobic, they moved into aerobic, was 53%, whereas the average decrease from 12 to 18 minutes was 5%, which shows that they're further doing it, but the body has not fully got rid of all the waste products produced by that anaerobic energy system, which is lactic acid. Breathing rate. Review. The average breathing rate between the 3 clients pre-exercise was 17.6 breaths per minute. It began to increase, with the average breathing rate being 35.3 breaths per minute at the 12-minute mark, an increase of 49%. This then decreased to 34 breaths per minute at 16 minutes, a decrease of 3%. The average breathing rate from 2 to 4 minutes was 25.5, and the average percentage increase from 0 to 4 minutes was a rise of 47.5%. My null hypothesis for breathing rate was that it would increase to around 3 minutes and then begin to plateau for the remainder of the event. This is due to the fact that once the body has found a heart and breathing rate in which the muscles are receiving enough oxygen and can meet the demand of the environment and exercise, then it will stay there, as the heart has no need to increase the oxygen sent to the muscles, meaning the heart rate and breathing rate can plateau. In order to measure breathing rate, one of the group had to visually assess how much the person was breathing, but in order to make this easier, We made the client doing the exercise emphasize her breathing rate so we can see it easier. As per the normative data for breathing rate, according to Dr. Artur Rakimov on August the 9th, 2018 on the website normalbreathing.com, is around 12 to 16 breaths per minute. Comparing this to our results, the average breathing rate was 17.6 breaths. This portrays a small anticipatory rise. This occurs due to the emotional release of noradrenaline, which is controlled by the hypothalamus. The sensory neurons inside of our body detect an increase in the noradrenaline and send an impulse to the central nervous system, secreting the noradrenaline into the bloodstream, increasing the beat rate of the SA node and therefore the heart in preparation of our exercise. Once exercise begins and increases, then breathing rate should increase in accordance to the workload given to the muscles, which should be small and is detected by the peripheral receptors in the body. This is backed up by our graph, as from minutes 2 to 4, the average breathing rate increases to 25.5, an increase in 47.5%. This increase is due to the fact that the clients are beginning to work in steady state exercise, and in order for the working muscles to carry on contracting, they need to receive oxygen, meaning an increasing breathing rate will occur. Once this process has occurred and the heart has found the perfect heart rate and breathing rate to supply muscles to supply oxygen to the working muscles, then they will plateau as no more oxygen is needed in the working muscles. During the periods of 33 to 20 minutes, this occurs, supporting my hypothesis. The average breathing rate between 12 to 60 minutes has a fluctuation of 4%, matching my hypothesis about breathing rate increasing and then plateauing, as just stated. However, one of the graphs doesn't match normative data. Evelyn's breathing rate increases past the normative data up until 6 minutes. This may be due to the idea that she is not working aerobically, but is in fact working anaerobically. We can support this via her heart rate graph that increases up to 9 minutes. This shows that she is working anaerobic, as if it were aerobic, the heart rate would not need to increase as oxygen is not needed in the muscles. However, in anaerobic work, an increase in oxygen is needed as the muscles carry on to work at an increased intensity, and the only way they can do this is through increased oxygen consumption. This can be achieved by increasing the heart rate and breathing rate. So, oxygen saturation review. The average oxygen saturation before exercise is 99%. The average oxygen saturation from 4 to 6 minutes is 96.7%. The average decrease from 0 to 6 minutes is 2.4%. The average oxygen saturation from 8 to 11 minutes is 96.6%. The average oxygen saturation decrease from 6 to 11 minutes is less than 1%. And then the average oxygen consumption from 17 to 20 minutes is 89.5%. The Borg scale review. Average from 1 to 3 minutes is 8. Perceived work. The average from 6 to 8 minutes is 10. The average from 10 to 13 is 11.3. And the average from 18 to 20 is 11.4. And the common trend is that it should increase as it goes up to 3 minutes, but then from there on it shouldn't increase too much as the heart rate and as nothing's changing, the body's just going over the same process over and over again. But as the muscles tire, and in case their breathing rate hasn't plateaued and they're taking in less oxygen, then they may begin to feel it going a bit harder, such as in O'Shean's graph. Blood pressure review. The average systolic blood pressure pre-exercise was 125.3. The average systolic blood pressure from 8 to 12 minutes is 102.7. The average systolic blood pressure decreases from 0 to 12 minutes is 18. The average diastolic blood pressure pre-exercise is 88.3. The average diastolic blood pressure from 8 to 12 minutes is 63.7. The average decrease in diastolic blood pressure from 0 to 12 minutes is 26.4. So, do I accept my hypothesis? Overall, my 3 null hypotheses were correct, and I fully accept our hypothesis for heart rate and breathing rate, but partially lactate. So, for heart rate, our null hypothesis stated the idea that the heart rate would increase up until 3 minutes, and then plateau for the remainder of the event. In addition, we also said that an anticipatory rise would occur, and that the heart rate would drop back down to normal rapidly afterwards. The results we gathered lined up with normative data, with an example of the normative data being, the more fit you are, the faster your recovery. Your heart rate drops most sharply after the event, after the minute you stop exercising, and then it should fall to about 20 beats per minute after that, and that's by Beckley Wellness. A couple of experimentals had to be used, such as where we discovered Morgan's had been working in the anaerobic energy system, and we had to find out why. This may have been because she was working in an anaerobic training zone, and in order to keep working the muscles, she needed an increase in oxygen every time they contracted, thus increasing the oxygen sent to the muscles via the heart rate and breathing rate. So for breathing rate, our null hypothesis was that breathing rate would increase slightly before exercise due to an anticipated rise, before further increasing for 3 minutes once the exercise had started. Once it hit 3 minutes, we expected the breathing rate to plateau for the remainder of the event. Once it had finished, we expected an instant decrease of breathing rate, as there would be no waste products to remove, as oxygen had been taken in throughout the event constantly, removing the waste products produced, which was hydrogen and carbon dioxide. From our results, I can identify this is what happened. An example of it being in the same is the fact that average breathing rate for our experimental experiment pre-exercise was 17.6, a slight increase than the normative data by Dr. Artur Rakimov on August the 9th, 2018 on the website normalbreathing.com, who suggests that it's 12 to 16 breaths per minute. We had to use one experimental method, which involved figuring out why Evelyn's breathing rate increased up to 52 over the 3-minute period to the 6-minute point. Looking at a heart rate graph, we identified due to it being an increase in heart rate and working in the anaerobic training zone rather than aerobic, which forces the body to take in more oxygen so that the muscles can carry on respiring. And for the lactate energy system, it was partially correct, proven by our experiment. We predicted that there would be no lactate in the bloodstream at all, due to them working aerobically and producing no byproducts. However, all 3 of our clients showed lactic acid in their bloodstream at some point during the experiment. While this may prove our hypothesis wrong, according to PT Direct, lactic acid is not produced from aerobic exercise, suggesting we conducted our experiment wrong, or just the idea that the clients were working too hard, forcing the lactic acid to be produced, as there's no presence of oxygen. However, once they all did enter steady-state exercise, the lactate levels in their blood began to drop, as in exercise the breathing rate was, supplying the muscles with more oxygen and removing all of that waste products, reducing the overall levels in the readings. So here is my bibliography.